Linearization and differentials. What I want you to realize is there's not really much that's new here. New notation and maybe some new ways of looking at some problems that make things a little confusing, but no new ideas. All right? What's essentially going on in this whole section is the idea that if our function, let's graph a function here, has a derivative, so we say it's differentiable. Right? If it's, say, differentiable at this point, that means we have a nice tangent line. And we know that a tangent line means that when we zoom in here, the function and the tangent line are in good agreement. So what linearization and differentials do is they say, well, if I know what's going on at this particular point, I can label it. Let's call it A. And so the y-coordinate would be f of A. And I know what the slope is there, then I have a pretty good idea what's going on over here. All right? Because I know the slope. The slope is given by f prime of A. So that tells me how steep my function is. And so if I move a little way away from the point A here, where I know what's going on, I can sort of predict what's going to happen on the function by using the idea of the slope. So if I take a small step of, say, 1, then the slope tells me how much my function should rise. That's the only new idea, and it's not a new one at all. All right. So there are the two words here in the title, linearization. Well, linearization, this is the same thing as a tangent line. Right? We've practiced taking the tangent line many times by now. And a differential, this gets back to an old idea, which says the slope of the secant line is approximately the same as the slope of the tangent line. Particularly if we use 2 points that are nearby each other, we'll get a good approximation of the slope of the tangent line. So these are old ideas with new words. All right. Let's get into the idea a little more carefully about linearization. It's just the tangent line. Okay, so tangent line. Got my graph. All right. If I want to find a tangent line, say at this location on the graph, what do I need to do? Well, I need the coordinates to that point. And like for the equation of any line, right, there it is in slope-intercept form. I can also rewrite this line as y equals, I'm going to move the y0 over to the right side. Okay, and so if it's a tangent, that's generic equation of any line. If I want the tangent line, then I need to know what the slope is at this particular location. And to find that slope, we use the derivative. So we can evaluate the derivative at this point to get this value m. Okay, so in order to come up with the y-coordinate here, we evaluate our function. And in order to find the slope of the tangent line here, we evaluate our derivative. So now I'm going to take those ingredients and put them into the equation over here. We get y equals y0. Well, that's the same as the function evaluated at x0 plus f prime at x0 times x minus x0. So x0 here is a number. Right? This is the equation of a tangent line. Maybe it looks a little different than the kind of equation we've been using because we often use slope-intercept form like mx plus b, or we start here with the point-slope form. But it's exactly the same equation, just rearranged. Right. Now what goes on in this chapter when we talk about linearization? Well, we give this tangent line equation a new name. And we also change the name of this point a little bit. That's the common notation. So we're going to call this point A. So x0 is A. And then we give this a new name. We call this the linearization L of x at A. What does that look like? It says L of x is equal to the function value plus the derivative times x minus A. So A is a number, and when we use the function, we get a number here, a number here, a number here for A. So this gives us a typical equation of a line. Right? L of x is the linearization of f at A. So L of x is this line. It's just the tangent line. And much of the idea in this whole chapter, in this section, is that the linearization and the actual graph are in pretty good agreement as long as we stay nearby the point of tangency, as long as we stay close to x equals A. How could we use that? Well, let's look at an example of computing on linearization first. So we want to find the linearization of f of x equals the square root of x at A equals 100. So translated, what we're doing here, I'm taking my square root graph, going to the point on the graph where the x-coordinate is 100, and I'm working out the equation of the tangent line to the graph at this point. Once I have that equation, I can do some things with it, but let's get the linearization first. Same as the equation of the tangent line. You can either work it out old school, or you can work it out with this new formula. Let's do it both ways, just to see. Right. The derivative here, I need that to get my slope. This is x to the 1/2, so I'll get 1/2 x to the minus 1/2, or 1 over 2 square root of x. And I need to evaluate the function and the derivative at A equals 100. So f of A is f of 100, or square root 100, is 10. And the slope, f prime of A, is 1 over 2 square root 100. It's 1/20th. So my tangent line, no matter what else I do here, has to go through the point 100, 10, and it has slope 1/20th. Okay. Now if I do this the old school way, right, I just work it out from hand. Right? I'm going to start with slope-intercept form. Put in the coordinates of my point. The y value is 10, the x value is 100, and the slope is 1/20th. Now we could go ahead and reduce this to a slope-intercept form, but it turns out for many of the problems in this section, it's a little more convenient to leave it like this. But this is just the equation of the tangent line. In this section, it gets a new name. That is L of x. We call that the linearization of the square root function at the point 100. New way is to start with our template for finding the linearization, right? And then just to plug in. So this says we get L of x equals f of 100 plus f prime at 100 times x minus 100. Well, we know f of 100 is square root 100 plus the derivative 1 over 2 square root 100 times x minus 100. So we get 10 plus 1/20th times x minus 100. So old school way, find the equation of the tangent line. New way, use the template, plug things in, and get the same kind of equation for the tangent line. But now we call it linearization. What can we do with it? Well, the idea here is I've got my square root function. I'm over here at, say, a equals 100, where I know the value of the square root is 10. So if I know what's going on here, and I also know the slope is 1/20th, slope of the tangent line right there, I ought to be able to tell you what's going on at, say, at 99, right? So if I go over here to 99, and the slope is, that's one step to the left, 1 unit, my slope tells me I should go down 1/20th. So the square root of 99 here is going to be approximately 10 minus 1/20th. One step to the left, I have to go downhill by 1/20th. So here's an example. Let's approximate square root 98 using linearization. Some of the problems in the homework and the web work, they don't say much more than that. The idea here is, if I don't have a calculator, then how can I get a good idea of what square root 98 is going to look like? Well, I know 98 is close to 100, so square root 98 should be in the vicinity of square root 100. So about 10. That's a no-brainer. But how can we do better? Well, since we know everything about what happens at 100, we can linearize. So I'm going to take my square root function, and I'm going to replace it as we did above by the linearization equation. So here's the square root equation. And the linearization equation we've seen is 10 plus 1/20th times x minus 100. So the square root of 98 would be approximately, so I go over here to 98, and if I had a calculator, I would just push the square root button and it would tell me what square root of 98 is and give me lots of decimals. Since I don't have a calculator, I'm instead going to look at the line, because that's easy to compute. So this is approximately L of 98. So we're going to use the linearization, which is 10 plus 1/20th times 98 minus 100 is 10 plus negative 2 over 20, 9.9. So negative 2 over 20 is minus 1/10. So the square root of 98 is about 9.9. The actual true value, if we pick up our calculator, so it is really close to 9.9. Okay. What about differentials? Differentials are again saying pretty much the same exact thing. New notation, might be a little confusing, but nothing very new. Okay, the differential again is based on the idea of the tangent line, about taking the derivative. So let's draw a picture. If I'm at some location, this time I'm going to call it x, and I know what's going on my graph of f here at this point x. So that means it's pretty easy to calculate the derivative and get a value for it. It's very easy to calculate the function value. Then I can approximate, I can figure out what's happening at nearby points by scrapping the function and just following this tangent line. Okay. Another way to think about this is if we want to go to some nearby point, I'm going to call it x plus delta x. So delta x here represents a small change. Right. Well, how can I predict the value of f of x plus delta x? Okay. So the y coordinate here. Another way to think about this is, well, look, if I've got 2 points on the curve, we're talking about, one thing we can talk about is the slope of a secant line. And we know from our exploration of derivatives that the slope of the secant line is about the same as the slope of the tangent line. Right? So what is the slope of the secant line here? Well, if this has y-coordinate f of x, then the secant line right, and that's going to be rise over run. And that is going to be approximately the same as the slope of the tangent line, particularly if delta x is very small. And this is, of course, f prime at x. So nothing new here either. Okay. The slope of the secant line is approximately the same as the slope of the tangent line. What's new here is that we introduce a lot of new notation and talk about the problems a little bit differently, and they get confusing. All right. So what we're usually interested in here is from this location on the graph, if we move in the x direction, how much do we expect to move in the y direction? All right, so some notation. This quantity right here in the numerator, we call this the true change in y. Right, that's the difference between the y coordinates here. And that distance, we call it delta y. So delta y is the same as this numerator here. It represents the true amount of change in the function f. And if you need to calculate delta y, then what you need to do is just grab the two x values here, plug into f, get the 2 points on the graph, and then take the difference to find the change in y. So the whole differential idea says that delta y over delta x is approximately the same as f prime of x. Change in y over the change in x is about the same as f prime of x. If we rearrange this equation, we get delta y is approximately f prime of x times delta x. I like to say with this equation that the rise in the function is about the same as the slope times the run. Okay. Now some more new notation. A differential is just another way to write this approximation. Right? So we call this side here dy. Right? So what this represents is the linear change, or the change in following the tangent line, right? The linear change in the function. It's just what we get by following the tangent line instead of following the actual curve. Right? And to make things extra confusing, we take this delta x and we replace it by dx. So this guy right here is the same as delta x. But dy and delta y are not the same. So delta y is the true change in f. Okay. So that's going to be f of x plus delta x minus f of x. And dy is let's call it the linear change in f, which we calculate from this formula. It's the slope of the tangent line times the change in x. So as x changes from x to x plus delta x, we're on our graph here, the true delta y is this distance, okay, which we get by evaluating the function at these two x points and taking the difference. Dy, right, is how much the function, the tangent, increases as we move from x to x plus delta x. So that distance It's almost the same. So this little bit here, that's delta y. The larger triangle, that's dy. dy represents the linear change. If we follow the slope, starting at the point x, we follow the tangent line, for a distance of delta x in the horizontal direction, dy is the amount of rise that we get. Let's see a couple examples. We're going to stick with the square root function and see how this relates to linearization. So let's say find the differential of f of x equals the square root of x at x equals, well, not at x equals anywhere, let's just find it. So dy is equal to f prime of x dx. The derivative here, if this is x to the 1/2, the derivative is 1/2 x to the minus 1/2, or 1 over 2 square root of x dx. So this is called the differential. Right? It's a funny looking equation, but it's new notation for an old idea, which basically says that the rise in the function is equal to the slope times the run. Okay. So let's find the differential. Same problem. At x equals 100. So we'll get dy equals 1 over 2 square root 100 times dx, or 1/20th dx. If you watch the bit about the linearization, it's the same number, 1/20th, that came up as the slope in that problem. Right. So this is predicting that the square root curve, right, around x equals 100 is going to change 1/20th for each increase of 1 in x. So suppose we want to estimate the square root of 98 with differentials. Again, the idea here is we're going to go to a point on the graph where we understand what the square root curve is doing. So we're going to go over to 100. And at x equals 100, we calculate the differential. So we already did that. We know that dy is 1/20th dx. At 100, we know the value of square root is 10. Right, because square root 100 is 10. Now what's going on at 98? So suppose I don't have my calculator handy, so I go over here to 98. And that tells me that, look, in the x direction, I've made a change of -2. So the change I expect in the y direction, more or less, what we're doing is we're using the tangent here, according to the differential, is going to be 1/20th, right? That's just the derivative here, evaluated at 100, times dx. Or more generally, dy equals f prime of x dx. The x I'm using has nothing to do with 98. The x I'm using is over here at 100. Right? I use x equals 100 because I understand what the height of the graph is here and what the slope is. They're easy to calculate at 100, not so easy at 98. Okay. So we plug in x equals 100 here, and we get this equation. Now we're going to take a step of 2 to the left, so that tells me dx, the change in x, is -2. Remember, dx is the same as delta x. So the approximate change in y, or the linear change in y, is going to be 1/20th times -2, or -1/10. So when we take a step to the left, the change in y we expect to be about -1/10. So the new y, which is about the square root of 98, will be the old value over here at 100, which we knew to be 10, plus dy, or 10 minus 1/10, or again 9.9. Hopefully that video gives you some idea of what's going on with linearization and differentials. New notation, old ideas.